Obviously, our problems can get more difficult. In example 3, we're going to utilize some geometry. Example 3 asks us to find the dimensions of a cylindrical barrel with a volume of 50 cubic feet, which minimizes the materials needed to construct it. I'm going to do my best to draw a cylindrical barrel or a cylinder in general, but we're going to have a cylinder. Think of a can. And so when I'm trying to find the materials, I'm actually looking at the surface area of this cylinder. It does have a top, it has a bottom, and then the side obviously goes all the way around. So the top, the bottom, and the side. That's the surface area. And we want this barrel to have a volume of 50 cubic feet. We can make the cylinder, really short and wide, and it could have 50 cubic feet. Or we could make the cylinder taller and thinner and have the volume 50 cubic feet. We have to figure out the dimensions of the cylinder whose volume is 50 cubic feet, which minimizes the materials needed to construct it. In order to find those dimensions, we need two geometric formulas. The first of the geometric formulas is the volume of a cylindrical barrel, or the volume of a cylinder. And the volume of a cylinder is pi r squared multiplied times the height. Radius of the top and bottom discs is being squared. Notice you get essentially the area of a circle and then multiplied by a height dimension. That's the volume. Now we know the volume is 50 cubic feet. Since we know the volume is 50 cubic feet, that's our constraint. We're given the fact that the volume's got to be 50 cubic feet. And we want to minimize the materials. Well, the materials are going to be my surface area. And the way the surface area goes is you find the surface area of the top circle, that's pi r squared, and then you add the surface area of the bottom circle, that's again pi r squared. So we can call that 2 pi r squared for the top circle and the bottom circle. And then the outer ring. Now the outer ring has height of h, and it has length of the circumference of the circle, that is 2 pi r. So the surface area is that function there, 2 pi r squared plus 2 pi r h. If you ever have any questions about that, you can always just look it up too. So we want to minimize the surface area because that's where my materials are going, with the constraint that the volume has to be 50. You can either solve for h or r. I think in this case, it's a little bit easier to solve for h. So h is equal to 50 divided by pi r squared. And then I'm going to plug in 50 pi divided by pi r squared into the h for my surface area equation. So S for surface area is 2 pi r squared plus 2 pi r times h. And again, I'm replacing h with 50 over pi r squared. There's a few things that we can do here to just simplify this equation with the s. We can multiply things through on this second term. 2 pi times 50 divided by pi r squared, 2 pi r times 50 divided by pi r squared. The pi here in front can cancel with the pi in the denominator. And then 1 copy of r can cancel with 1 copy of r in the denominator. 2 times 50 becomes 100. And our equation becomes 2 pi r squared plus 100 divided by r. We want to find where the minimum is. The way we do that is we take a derivative. Derivative is 4 pi r plus, you can think of this as r to the minus 1. So when you take negative 1 out front, you get negative 100 divided by r to the negative 2, or excuse me, if you're multiplying, it'd be times r to the negative 2, but since you're dividing, it's divided by r squared. Let's go ahead and set that equal to 0 and solve to find our critical values. Let's go ahead and multiply both sides by r squared. By the way, I know I can do that and get rid of this denominator because I know r is not going to be 0. If r is 0, then my cylinder has no value. So I can multiply by r squared, assuming that the r is not 0. If I do that, r squared times 0 becomes 0. R squared times 4 pi r becomes 4 pi r to the third. And then 100 divided by r squared times r squared would just be minus 100. We can solve this. It's not real pretty, but we can solve it. So I add 100 to both sides, then I divide by 4. I would end up with 25 equals, actually let's divide by 4 pi. I would end up with 25 over pi equals r to the third. And therefore, r would have to be the cube root. And it's going to be positive because of the context of the problem. It would be the cube root of 25 over pi. Oh, I said I cubed. I want cube root, so 1/3 power. That's not a really nice number to deal with, but we can, in fact, plug this in to our calculators and get an approximate answer if we like. So 25 over pi to the 1/3 power, or to the cube root, would give me about 1.996. So pretty close to 2 for my R. And once I know that, I could, if I wanted to, show that I am going to get a minimum by taking a second derivative and plugging it in, but you can trust me on this, you do get a minimum. And now we're going to figure out the actual minimum and then also the H. Don't forget, we haven't dealt with the H yet. The constraint equation, put that up top. The constraint equation is the one that gives me my H. I just plug in this R. Now I'm gonna just round things to like 3 decimal places. That's not perfect, but you can do it. If I take 50 divided by pi and divided also by 1.996 squared, I get an H of approximately 3.995. Again, I'm rounding to 3 decimal places. So the constraint would be that the radius is about 2 and the height is about 4. So that's what's going to happen. That's where I'm going to get a minimum surface area. And if I actually want to find that surface area, we take 2 pi times r squared, take 1.996 squared, plus 2 pi r, 1.996, multiplied times h, 3.995. You can plug that into your calculator and you get a surface area of approximately 75.135. Now that's a surface area, so that would be in square feet, whereas the height would have been in feet and the radius would have also been in feet. So you get a minimum surface area of 75.135 square feet when the radius is about 1.996 and the height is about 3.995. By the way, if you would like to check your answer and check that this makes sense, you can plug in the radius and the height into your constraint equation, and hopefully the pi r squared times h gets you close to 50. In fact, I've done this and you get very, very close to 50. It's off a little bit because we rounded our numbers. So there you go. The minimum surface area is about 75.135 square feet. And that happens when the radius of the cylinder is about 1.996 feet and the height of the cylinder about 3.995 feet. So you can see that this type of thing comes from the minimizing a surface area, which is a geometric formula, with a constraint, which is a volume, essentially, formula. These things can be really useful. Think about if you're trying to ship a bunch of containers that are all 50 cubic feet, and you want to figure out how to manufacture a big drum that minimizes your cost to manufacture these, well, there is a proper radius and height. And you can kind of, if you want to sketch it out and see how well that fits about what your concept of a normal barrel is. Another very common optimization problem is constructing rectangular pins. Again, you're going to need some ideas from geometry because we're talking about rectangular pins. And you have, in this case, 3,600 feet of fencing. And so you want to maximize area of these rectangular pins, and you have 3,600 feet of fencing. I want you to go ahead and try this one on your own. Pause the video. In the next video, we'll show you how it's solved.